Hey everyone, it's Mr. Glover here. Ready to do our next video lesson. So today we're going to talk about permutations again. But the thing that's different this time is that we're going to have some repeated elements. So you might have some of the same letters or some of the same numbers, and we have to figure out a way to deal with organizing those letters when some of them might actually be the same. So recall the number of permutations of A, B, and C is 6. And that comes from the fact that there's 3 distinct elements. We could either multiply 3 by 2 by 1 to get us 6, or we could have done 3 permutation 2 to get 6. But what if we change the letters? What if we change a C to an A? Then the letters become A, B, and A, and that's going to greatly restrict the number of possible outcomes. If we want to actually list them, we could have A, B, we could have A, B, A, or we could have B, A, A. But that's it. There's only the 3 permutations. Because we could have BAA twice, we could have ABA twice, or AAB twice, but they're not different. They're the same word. Or just AB, ABA, and BAA, which is 3 permutations. There are 3 elements, but only 2 are distinct. And the way of thinking of distinct is if you put them in a hat and pulled one out, could you tell the difference between the 2? If not, they're not really distinct elements. From the first case, there are 3 factorial, 3 times 2 times 1 equals 6 permutations. For the second case, if we take that 3 factorial and we divide it by 2 factorial, it'll get us 3 times 2 factorial over 2 factorial. The 2 factorials will cancel and we'll be left with just 3. This is the number of permutations we had when we repeated a digit. And if you're wondering why we did this, well, 2 factorial ties into the number of A's we had. 3 is the number of letters we had. And so we've kind of indirectly figured out a strategy for dealing with this, and that's actually the formula. So the number of permutations of n objects with r identical objects is n factorial over r factorial, where r is just the number of repeated things. So this is actually a really simple formula to use, as long as you have the right situation to use it. So how many permutations are there of the numbers 1, 2, 3, and 2? We have 4 numbers. So n is going to equal 4. However, we've got 2 2's. So r is going to be 2. What we can do then is we can go n factorial over r factorial. N is 4 and r is 2. This equals 4 times 3 times 2 factorial over 2 factorial, which is going to be 4 times 3, or 12. So 12 permutations of 1, 2, 3, and 2. It would be more if we had 1, 2, 3, and 4, but since we have repeated elements, we've got to divide by them to eliminate the duplicate combinations. There are 8 cans of soup on the shelf. 3 cans contain tomato soup, while the other 5 cans are different. How many ways can be arranged in a row? Well, if we have n equals 8 cans of soup, and we have 5 cans that are different, but 3 cans that are the same, r equals 3 for the repeated elements. So this simply works out to 8 factorial over 3 factorial. And then you can either calculate it by hand, or you could use a graphing calculator. If you want to do it by hand, it's going to work out to 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. Your 3 factorials cancel, and you just have to multiply 8 by 7 times 6 times 5 times 4, and you will get 6,720 permutations. What if there's more than one repeated element, though? What if instead of 3 cans of soup being the same, what if we had 3 cans of tomato and 3 cans of, I don't know, mushroom soup, but some of the others were different? In terms of numbers, what if we had a combination like 1, 1, 2, 3, 4, 4? In terms of letters, what if we had a word like tooth, where we have 2 T's and 2 O's? Turns out we follow the exact same process. So I'm going to read this out to you, and it's going to sound really confusing because it's very general, but you'll see that this is actually a fairly simple formula to use. So instead of n objects with n factorial objects of one kind, and one objects of one kind, and 2 objects of another kind, and 3 objects of a third kind, and so on for k kinds of objects, the number of permutations is n factorial over n1 factorial times n2 factorial times n3 factorial times all repeated numbers until you reach the final one, where n1 plus n2 plus n3 all the way to nk equals n. So what this is saying, and it's really general, is if you've got n objects, let's say you had 10 objects, and n1 of them are one kind, so let's say you had 2 T's, and 2 of them are another kind, like 2 O's, you just take the total number for tooth. It's going to be 1, 2, 3, 4, 5 factorial over the number of O's, which is 2. So 2 factorial over the number of T's, which is 2 factorial. So you basically take the total number factorial, divide it by however many things are repeated, all multiplied together, and all factorials. So how many permutations are there of A, B, 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 and C? Well, we've got 1, 2, 3, 4, 5, 6 letters. But we have 2 A's, so n1 equals 2, and we have 3 B's, so n2 equals 3. So we want the number of permutations. N factorial over n1 factorial times n2 factorial is going to be the total number of letters, 6 factorial, over the repeated A's, 2 factorial, times the repeated B's, 3 factorial. And this one, I think we'll just use a calculator for, but you can do it by hand. It's going to work out to 60 permutations. All right, how many permutations can be made from the following? I guess we're going to do tooth again. So foot, there's 4 letters, so n equals 4. But there's 2 O's, so r equals 2. Number of permutations is going to be 4 factorial over 2 factorial, which is going to work out to 12. For the other question, for tooth, like we just did, we've got 5 letters this time, so n equals 5. 2 T's, so n1 equals 2, and we have 2 O's, so n2 equals 2. Number of total permutations is going to be 5 factorial over 2 factorial times 2 factorial. Which would be 30 permutations. So it would be awfully convenient if we can extend this to any number of objects picked from the original set. So let's find out, can we use this for a portion of the original word? So for example, like if I wanted to only use 2 letters of tooth, or if I only wanted to use 2 letters of foot, can we use the same trick? Well, if we were using the same trick, give the number of permutations of A, B, R, and A, we would have 4 letters, and we would have 2 that are repeated. So in theory, we could go for permutation 1 and then divide it by the repeated letters, which would be 2 factorial. But if we do this, we're going to end up with 2 permutations. If we actually list out the number of 1-letter combinations, we would have A, B, R, which is 3 permutations. So does it work? No, it doesn't work. There is a way to do it this way, but it's very complicated because you have to essentially break it into cases where case 1 would be where you use 1 of the repeated letters. Case 2 would be where you use 2 of them. Case 3 would be where you use 3 of them. And you have to kind of build the problem up that way. Many times it's much easier to just list them all out. So that's what we're going to do. Please make sure that you read through this. It does not work. This is not how you would go about solving these. What I would do is just list them all out. So if we want to use 2-letter combinations, well, we could have AB, we could have AR, we could have AA. We could have BA, we could have BR, we could have RA, or we could have RB, but that's it. That leaves us with 7 permutations. If you wanted to solve this using permutations, you could split this up into combinations with 1 letter, which will work out to 1, and then you could split it up into, or sorry, it'll work out to 6, and then you could split it up into combinations with 2 A's, which would be 1, and 6 plus 1 gets you to 7. But it's much easier to just list them. All right, a couple more problems for today. Rylan walks a total of 9 blocks to school every day. He always walks 5 blocks west and 4 blocks north. How many ways can Rylan walk to school? So if you think about this problem, he has choices when he wants to go west and when he wants to go north, right? He, let's say he starts down here and he's going to school over here. He could go all the way over in one shot and then all the way up in one shot. And maybe I'll highlight these. I think that would be a little better. So he could do this route, but he's not restricted to that route. He could also choose to go in kind of like a staircase pattern if that's what he wants to do. He's got many different possible ways of walking to school. He could go halfway up and then kind of take the staircase pattern, then go up. He's got all sorts of options. So the way that you have to solve this is you have to think about every choice of going west or going north as being a decision. And essentially, you're just arranging when you made those decisions. When did you go north? When did you go west? This is a permutation problem. Essentially, if you break this down, he's going 5 blocks west, 4 blocks north, but he's traveling a total of 9 blocks total. That's going to be n. That's the number of blocks he travels. He's going 5 blocks west. 5 blocks west. Well, that's one of your repeated elements. You're repeating that 5 times. So that's, we could call it n1. He's also going 4 blocks north. Again, those are repeated elements. Call it n2. You want to figure out the number of ways that he could possibly go to school? Well, n factorial over n1 factorial times n2 factorial. That is going to equal 9 factorial over 5 factorial times 4 factorial. That's going to be 126 rows. All right, and one more problem. Typical bag of Skittles has 8 red, 7 yellow, 4 green, 6 orange, 3 purple. Chastity sneaks a bag of Skittles into class. How many different ways could she eat the Skittles? Well, the first thing you've got to do is you've got to count up how many different Skittles are in the bag. We've got 8 plus 7 plus 4 plus 6 plus 3. There's going to be 28 total Skittles. That's your N. That's the number of Skittles in the bag. We've got 8 red. We have 7 yellow. We have 4 green, 6 orange, and 3 purple. So this is like N1, N2, N3, N4, and N5. They're all repeated elements. The number of permutations is going to be n factorial over n1 factorial, n2 factorial, n3 factorial, n4 factorial, n5 factorial. It's going to be 28 factorial all over. 8 factorial times 7 factorial times 4 factorial times 6 factorial times 3 factorial. This is going to be one that you probably want to do on a calculator, because otherwise you will have a lot of things being multiplied together. This works out to 1.45 times 10 to the 16 permutations. So you could eat that bag of Skittles a different way every day for the rest of your life, and you will still never reach the total number of permutations. You could probably eat a different bag of Skittles every minute for the rest of your life, and you still won't manage to have the exact same combination or the same order. So that is pretty much it for the notes today. The big idea is you take the total number of objects and then divide by the number of repeated objects for every single one that's repeated. I've got some problems for you. They're on page 266 of your textbook, questions 1 to 6 and question 9. They're all to do with repeated elements. The first few of them are already laid out for you, and then the rest of the questions you have to go and actually figure out what formula to use to solve them. So I think I'll stop the notes here. I hope everybody has a great rest of the day, and I will see you all tomorrow when we have our meeting. So take care. Bye for now.